Welcome back, folks. Still trying to connect the phasor domain representation to what you would actually measure on an oscilloscope. We're going to go backwards this time. We're going to start with the phasor, the phasor value. We're going to work back to the time domain expression, and then we're going to get that onto a time domain plot and then check it. Okay, so here's what I dreamed up for you this time. So here's our phasor, 3 at an angle of -90 degrees. And the phasor by itself doesn't have the frequency, so I had to give you the frequency as well. So that phasor is spinning at a frequency of 1.5 hertz. So it's going to go all the way around. Let's see, 3 at an angle at -90. So this is 3. It's going to start down here at -90. In 1 second, it's going to make it all the way around and then halfway around. So 1.5 seconds. So think of it as spinning. It's really fun to do this with my arms in a classroom. You get fingers and a webcam that I hope is spun the right way. We'll see. Okay, let's draw pictures instead. So on a phasor diagram, this phasor is going to look like this. Okay, so we have the real component and the imaginary component. And the phasor itself is going to point straight down. Right, that's -90. And it's going to have a length of 3. So as this spins clockwise, ultimately what I'm trying to do is get some intuition. As it spins clockwise on the time domain plot, it's going to start at 0, because that's where the point is along the real axis, and it's going to start to get more positive until it heads toward the positive peak of 3. That's what I would expect it to do. We'll see if that's what it actually does. Okay? So let's get the time domain expression. We need 3 pieces of information. We already have 2.5. We need the amplitude, we need the phase shift, and we need the angular frequency. We have the regular frequency, we need to turn it into an angular frequency. Okay, so let's say omega is equal to 2 pi f in this case. So we're going to get 2 pi times 1.5, also known as 3 pi. So what's that going to be, like 9 and change? 9.42. 9.42 radians per second. Okay, so that's really all we needed to do. Then we can just go ahead and write it. Let's call it a voltage. It could be a current. It could be a force, it could be a moment for all you MEs in the crowd. Some of this math translates nicely to just about anything in the natural world. Now I'm trying to think of examples in the unnatural world. We'll leave that as an exercise for you. Okay, so the peak value is 3. That just came right from the phasor. Cosine 9.42 as a coefficient of t. And then -90 degrees, again coming right from the phasor, and we'll call that volts. Call that volts there just to make it clear. Okay, so there's our time domain expression. Hey, that wasn't so bad, right? So that was the first thing we were trying to do. I'm not going to do that around the whole plot down here. Hey, look, it's almost like I put this down here anticipating having to do this. Okay, so in order to make the plot, really all we have to do now is evaluate this at a few different values. So I think the easiest one to evaluate it at is at t equals 0. So evaluate it a few times. So v at t equals 0 is going to be 3 cosine. This term's going to drop out because it's 0 times 9.42, and we're going to get -90 degrees. Okay, cosine of -90 is 0. All right, so that's all going to drop out to 0, and this whole thing is going to be 0 volts. Okay, so that tells me I'm going to take that, and let's go with this color. That's going to be one of our points right there. I'm going to make it nice and big for when I do the final reveal in a moment. Okay, so what are some other values? Well, like 1 would probably be easy enough. You know, it's much easier when you let a computer do this for you. 3 cosine 9.42 minus 90 degrees. Oh, well, okay, so here's a little bit of a problem. 9.42 is in radians per second. Right? We multiply it by 1 second times 1 second. Those seconds are going to drop off, and it's left in radians. And then we have this in degrees over here. Who would do such a thing? Electrical engineers. Electrical engineers would do this to you. And I'm going to do it to you too. Okay, so we got to be careful. This is in radians. This is in degrees. So we got to convert one to the other. And let's get a second line down here. 3 cosine 9.42. Negative 90 is really negative pi over 2, right? So if you're going to evaluate that cosine, just make sure you're consistent with your units inside, and also make sure your calculator's in the right mode, right? So let's see, 9.42 minus pi divided by 2. Okay, take the cosine of that, multiply by 3, and it's going to be pretty tiny, 14.3 millivolts. So that's on the smaller side for sure. And that's at 1 second. Right? So I'm going to come over here, and it's going to be somewhere in this neighborhood over there. What other times could we work out here? Okay, I'm gonna plop down 4 more points, but I'm gonna do that without you having to watch me fumble with a calculator. Hold on, folks. It's like magic. I love it every time I do it. Cuts out all the tedious stuff, hopefully, and doesn't hurt your understanding. So we're plugging in 0.2, 0.4, 0.6, 0.8, and I got these values out here, 2.85 volts, negative 1.76 volts, and it looks like we have some symmetry going on. Good stuff. All right, so let's go label those down here. So at 0.2 volts, right, I just changed that time along this column. At 0.2 volts, we've got 2.85. So let me get the right pen color back out here, 0.2. I've got 2.85, so that's going to be somewhere in this neighborhood, right? At 0.4, I have negative 1.76, so that's going to be somewhere down here. Okay, at 0.6, we're also down here. Okay, and then at 0.8, we're back up here. So it looks like we're going to follow a path that looks something like this. This is hand-drawn, so don't expect it to fall line on line by any means, but I think it'll be somewhat close. That's a little inartful there. It's a cosine, kind of. It's pretty good. Let me grab the cutout of the other one, and we'll see how good I did. Okay. Whoop, there's that, right? So that's the actual waveform that I based this all off of. And let's drop that there. Okay, so this is computer generated. This is Dave generated. And it looks like they line up fairly well. Okay, yeah, I don't have a perfect hand on that. All right, so if we have the phasor and we have the frequency information, we can work our way back to the time domain expression, okay, using what's called the inverse phasor transform. So this was 3 at an angle of negative 90 degrees, and we get down to there using the inverse phasor transform. Okay, and once we have that, it's just a matter of evaluating that function repeatedly and kind of doing a pretty junky job of drawing it, or having a computer do it for you, and you totally get style points for that. Okay, so I hope you're more comfortable with how we use complex numbers to represent cosines. And if we can represent cosines, we can also represent sines. We've got to be able to convert between the two. Maybe I should do that next. That's what we're doing next. New video. Hopefully this helped. Let me know. Stay tuned and good luck, folks.